This is example number 5 in our series here of using exponential generating functions to solve permutation type problems. And if you're wondering where the other video series are, if you just found this on YouTube, if you go to the website at digital-university.org, all the videos that we have there concerning counting problems, permutations, combinations, the 10 or 12 videos that we have on ordinary generating functions, and how we use those to solve some of the more difficult combination problems, plus our videos so far concerning exponential generating functions. They're all there in their proper order for you. Now, in this video, we want to continue with a similar theme as what we encountered in the last video. And that is, here we have three numerals. We want to use them repeatedly to form, say, a k-digit number. So we might have something like this: 1, 0, 2, 0, 1, 0, and so forth, so that we have a number here that has k digits in it. And each time we form a string like this of k digits comprised of these numerals here, 0, 1, and 2, we want to have it constructed so that if 1 appears in the string, it's going to be used an even number of times. Same thing for the numeral 2. So this is a little bit more stringent than the past video having these constraints. So what we do is write out the generating function. We want to know essentially now how many k permutations can we form from these three numbers, from these three different numbers. With the proviso that if this appears in any of the permutations, it has to appear an even number of times. Same thing for the numeral 2. So, as we did before, writing out the generating function. Now for 0, if it's going to be used, there's no restrictions on it. It may not be used any time in a particular string, or it might be used once or twice or whatever. So for 0, the generating function would be x to the 0, which is 1, in case it's not chosen at all, or it might be used once, so that would be x to the first over 1 factorial. These are permutations now, so we're working with exponential generating functions. Or 0 might be used twice. And in fact, we're not stating any upper limit as to the number of times that, for example, 0 can be used when we're constructing a k-digit number. So that means the generating sequence, the exponential generating sequence, just goes on out to 0, or goes on out to infinity. So it'd be like this. So this would be the generating function for 0. Now, for 1 and 2, if either of these numbers are going to be used in one of these k-digit numbers, they have to be used an even number of times. So we may not use them at all, which would be x to the 0, or that would be 1, plus, now here we would not have x to the first over 1 factorial, because that means that we would be using the numeral 1 one time. No, we only use it an even number of times. So we could have x to the 2 over 2 factorial. 2 is an even number, or it might be used 4 times. And again, there's no upper limit that is stated in the problem. The problem never stated, for example, well, perhaps in each of these different permutations, the number 1 could only appear at a maximum 4 times. If that was true, then the generating function would stop right here. But we're not putting any upper limit on it. So once again, the generating function continues on up to infinity. Like this. So that would be the generating function for the numeral 1. And it would also be the generating function for the numeral 2. Both of these, it states that if we're going to use these in a string, it has to be used an even number of times. So here are the 3 generating functions, the one for 0, the one that describes 1, and that same generating function is also for the numeral 2. Now, to describe the situation where we're using all 3 numerals together, then we multiply all the generating functions together. And we'll do that in just a minute here. When we do that, we multiply all the generating functions together, all 3 of them. What we want to know is what will be the coefficient of x to the k divided by k factorial, because that coefficient, that is what is going to tell us the number of k permutations we could make with these 3 numerals, where each permutation has an even number of 1s and an even number of 2s. Okay, now let's look at the top expression. That is the generating function for 0. That we know from our previous videos. We know what that is. That is just e to the x, right here. So this function is e to the x. So that is our generating function for 0. Now, what about this one? We have 1, and we have all of these even powers. In one of our earlier videos, I think it was titled Exponential Functions, How to Find the Coefficients, we demonstrated that if we have e to the x, got to get this in better focus. If we have e to the x plus e to the minus x divided by 2, that's equal to 1 plus, well, all of the numbers here now are even numbers. And again, we derived that in that video. It was not difficult to derive. It just basically stems from the fact that here is e to the x. E to the minus x has alternating plus and minus signs, like this. So if we add them together, the odd numbers cancel out, and we would have 2 times this, plus 2 times that, plus 2 times all the even numbers. So if we add them and divide by 2, we get this expression. So here then, in our problem, this generating function is e to the x plus e to the minus x divided by 2. You might know from calculus, that's the hyperbolic cosine function, but really that's not relevant to our problem here. What we want to be aware of is that this is the generating function for numeral 1, as also the generating function for numeral 2. This is the generating function for 0. Now what we do is we multiply all 3 of these generating functions together. So we're going to have e to the x times e to the x plus e to the minus x divided by 2 times this again. That's the generating function for 0. That's the generating function for 1. That's the generating function for 2. We want to consider all three numerals together. We multiply all the generating functions together. So we're going to have e to the x times this squared. So we can write it like that. And then, once we do this, once we modify this out, what we want to know is what is going to be the coefficient of x to the k divided by k factorial. And that will tell us the number of k permutations that we can make with these three numerals, and in each permutation, if one appears, it appears an even number of times. The same thing for the numeral 2. So let's go to here. Let's modify this out. We will have 4 q of e to the 2x plus 2 times e to the x times e to the minus x plus, this would be e to the minus 2x. And this would be e to the 0 when we multiply these together, which is 1. So we can just write this as a 2 in here. So we have this times e to the x. So if we multiply across, and we're going to have e to the 3x plus 2 times e to the x plus, this would be e to the minus x divided by 4. Now our problem is almost finished. What we need to do is, from this expression, determine what will be the coefficient of x to the k divided by k factorial. And what we went through in the earlier video, we've done it several times now, but we introduced it in the video titled Exponential Generating Functions, How to Find the Coefficients, that when we have e to the nx, that's equal to this expression here. So the coefficient of x to the k over k factorial is n to the k. So here, n is just equal to 3. So for here, for e to the 3x, that's just simply going to be then 3 to the k power. That will be the coefficient of x to the k over k factorial. Here, n is just 1, so it's just going to be one to the k power, which is 1. So that would be plus 2 times 1 plus 2. And then here we have e to the minus x. Now, in this, you may have noticed this from the previous videos, the coefficient of that is minus 1 to the k. Try to bring these into better focus. Okay, here is e to the x expanded out. E to the minus x is the same thing, except now what we're going to have is alternating minus and plus signs. So here, the coefficient of x to the k is going to be minus 1 to the k. When that's even, this will be a plus sign. When that's odd, this will be a minus sign. So for here, this will be plus minus 1 to the k. So this expression here, divided by 4, that is our coefficient of x to the k divided by k factorial. Got to get everything in focus at one time. From this expression here, this is the coefficient of x to the k divided by k factorial. So, for example, if we said, well, here we have these three digits, 0, 1, and 2, and we want to form, say, a 6-digit number, and when we do it, this has to be used an even number of times, the 2 has to be used an even number of times. How many ways can we do that? The answer would be 3 to the 6th plus 2. Negative 1 to the 6th is a positive number, so it would be 3 to the 6th plus 2 plus 1 plus 3 divided by 4. And that would be our answer. That would be the number of six-digit numbers that we could form from these three numbers here, using them repeatedly, and 1 is used an even number of times in each 6-digit string, and 2 is used an even number of times in each 6-digit string. So again, hopefully that's starting to make sense to you, how we apply exponential generating functions and the kind of manipulations that we had to do with them in order to solve permutation problems. Now what we're going to try and do in the next video is consider a problem that has the same kind of logic, only to be a more practical type of problem, and hopefully you'll find it interesting. So come back and join us for that video, and we'll try and solve another problem.